Alright, so what I want to do now, especially for those who are still stuck at airports all over the world, is record a brief lecture on some of the mathematics that we need to really understand Legos. I know a lot of you have different backgrounds, so I'm going to try to do interesting things, interesting twists on things you've already seen. And if I start getting out of the range of the camera or the writing becomes hard to see, cool, you're in a good position, so you'll just let me know. Okay, so there's two steps for a lot of the problems. If I give you something, step one is, can you find a way to solve it? Okay, I want to get my family from Williamstown to Tucson, Arizona. Can somebody give me a bad way to do this?
Drive.
Walk. Okay, walk. There we go. Walk, okay? That will get me there. Driving is also a very bad way with two kids, 4 and 6, going that many hours in the car. Okay? So just because a solution exists does not mean it is a good solution or a solution you want to execute. So step one is, can I solve the problem? If no solution exists, it's not worth trying to find a good solution or an optimal solution or an efficient solution. But if a solution exists, then you can ask, let me look at all the different ways of solving the problem, and let me try to find, of all the different ways, what is a good way to solve the problem. So Cameron and Kayla helped me prepare this lecture, so Cameron gave me these numbers. I want to consider the following addition problem. 7 minus 6 plus 1,000 minus 7 plus 1,200 minus 1,000 plus 2 million minus 1,200. What does this equal?
1,900,000.
Yeah, Cameron wasn't too nice to you. 994. Okay. How did you do that so quickly? Cancel. This is a telescoping sum. Hopefully you've seen telescoping sums in calculus. If you've taken calculus with me, you may not realize you've seen it, but I know I've lectured it. Okay? How else could I have solved this problem?
1 by 1.
1 and 1,000 minus 7 is 993. This would then be 200. Right? Dot, 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 dot. I don't want to do algebra in public. Okay? From a mathematical perspective, is there any difference between the two methods? Efficiency, however, there's a huge difference. They will both give you the answer. But in terms of actually doing the calculation and also making a mistake, you're much less likely to make a mistake with this method than with that method. So there's lots of different ways of looking at a problem. So telescoping sums is a great starting point. And again, it's arranging calculations in a more efficient manner. How many of you know anything about Babylonian mathematics? Everybody's hand should be up. It's hard to go a day without doing something involving Babylonian mathematics. Somebody give me an example of Babylonian mathematics that you're stuck with today. Yes?
Time? Is that...
Time. So in what sense?
That it's not base 10.
It's not base 10. What base did the Babylonians use? Base
60.
Base 60. There's lots of good reasons to use 60. 60 is a highly composite number. It factors, you can divide it by 2, by 3, by 4, by 5, by 6, 10, 15, lots of different things go into. Anybody an Isaac Asimov fan? Right. In either Foundations, it might be Foundations Edge, they talk about why there's 12 speakers, because 12 breaks into committees lots of different ways. So there's certain numbers that are highly composite. That's very good, when you have a primitive number system. You don't have decimals and whatnot and easy to work with. There's lots of different ways of breaking things up. So we're stuck with this for the hours and minutes. We're stuck with this for degrees on a circle. If you do advanced math, we don't measure things in degrees, we measure things in radians. And the reason is, if you do radians, the derivative of sine is cosine, the derivative of cosine is minus sine. It's not the case if you measure things in degrees. In degrees, you have a factor of 2 pi over 360 that you have to be careful about. But if you use radians, the derivatives of sine and cosine are locked together very nicely. So how many of you know 7 times 8 off the top of your head? Right. You should all know through your 10 by 10 table, right? How many of you know your 11s? Yeah, 11s is not that bad, okay? 12s. 12 starts to get a little shaky. A lot of people, 13s. Yeah, by 13s, very few people, 1 or 2, we basically stop and, for something like, 14 times 17, we break it up into smaller things and combine. What would the Babylonian children have to do? Well, what tables would the Babylonian children have to study?
60 by 60.
60 by 60, right? Aren't you glad you didn't take a winter study with me a couple 1,000 years ago? Right? So, how many multiplications would you have to remember if you're the Babylonian kids? Number of multiplications is 60 squared, or 3,600. Can we help those poor Babylonian kids at all? Anything we can do to help them? I mean, they're dead, but if they weren't, what could we do to help them?
We could count mirror images.
We could count mirror images. As x, y equals yx, the number is what?
1830
So how'd you get 1830?
minus 60 divided by 2 plus 60.
So there's lots of ways of looking at it. So we could take the 3,600, we could subtract off the 60 numbers that are perfect squares, right? Divide that by 2, and this will give me all the distinct pairs of x and y. And then we have to add back the squares. So this is now the same as 3 plus 60 over 2, or 1830. And the 1830 is probably cut off from the board. Is it getting it, or yes or no?
Cut off. So
Okay, that's fine. I'll write it over here. It is 1830.
hard to tell.
Okay, it's 1830. If you want another way of looking at this part over here, is I need to choose 2 numbers from 60. So another way, if you know binomial coefficients, it's 60 choose 2 plus 60 choose 1. And that's the number of ways to get pairs of numbers, because I don't care about order, and then that's the number of ways to just get perfect squares. Alright, so this still requires the Babylonian children to learn 1,830. Okay? Do you think that's going to happen? No. So what do the Babylonians do?
Factor?
I'm sorry?
Factor?
Then you have to know, but you still have to know all the primes, and there's a lot of primes. And then you'd have to develop elementary number theory. So if you're not going to memorize everything, what are you going to have to do?
Look it up each time.
Look it up. So you have lookup tables. And again, just because a computation is easy does not mean you want to do it. I know several students of mine have had that experience on exams, right? So if you can look something up, it's a lot nicer. What is the problem with Babylonian lookup tables?
A lot of space.
Yes, why do they take up a lot of space?
A lot of numbers.
Okay, so one is a lot of numbers, so one is big. There's another issue.
No paper.
Yeah, clay tablets. Right? I mean, this is beautiful. Look at all these pieces of paper I can carry. It's wonderful. I can use tech, I can print things out, it's nice. You're lugging around clay tablets, right? So you have to first build the clay tablets. It's hard to mass produce. And you've got to lug that around. Okay, let me pull out my 49's tablet. It's not going to be very easy or very accessible. So the Babylonians needed a better way to multiply. Do they have a way? Absolutely. Is it an efficient, practical way? No. So the Babylonians had something very clever. So the first idea of a lookup table is one of the most important concepts in modern engineering. I'm assuming by now almost everybody in this class has a cell phone, or if not, has a friend who has a cell phone. The cell phone, I mean, if you look at the power, the computational power of the cell phone, it's staggering. But for a lot of the mathematical computations, it actually has lookup tables. So it doesn't have to compute things, it can just pull in the value. If you ask the Babylonians how to multiply x times y, smart Babylonians would actually do the following. Okay? Does this look like an improvement? No. This looks like we have taken a major step backwards. Right? What lookup tables do I need now? I only need lookup tables for squares. I have to be able to subtract. Subtracting is easy. I have to be able to divide by 2. Dividing by 2 is not that bad, especially if you work binary. But of course, the Babylonians were not doing that. That's the cause of all the problem, right? So what we've done is we've traded problems. If you just ask me theoretically, which would I rather do? I would rather view x times y like this than like this. But from an implementation perspective, what do I need to actually do the computation? This is much better with the systems I have in place. And it's amazing the advantage this has. Now you have more operations. You have 3 squares, 2 subtractions, and a division. Okay? That's much better than one big multiplication like that. So this is a major theme. Do a lot of small, simple problems. I would much rather do a lot of small, simple problems and combine them. Now, one of the themes of this class is parallelization. Could this problem be parallelized at all? Yeah, which parts could be parallelized?
Do all the squares at once.
You could do all the squares at once. You could have, basically 3 different Babylonians who are given, one is given x plus y, one is given x, one is given y, and they could calculate the squares. Could we parallelize the subtraction? No.
Because you'd have to use the x squared in both.
Right. The only way we could parallelize the subtraction is maybe I subtract off 1/2 x squared here and 1/2 x squared. That's not a good thing to do. So some parts of this problem could be parallelized and would lead to great efficiencies. Okay. For the most part, I don't think they were really parallelizing the squaring over here. But that is something you could do, and that's something I want you to be watching for whenever you see stuff now. How can I make the calculation faster? So the rule of thumb is basically every 2 years your computer system doubles in power or halves in cost. And so the better system you have, the more you ask it to do. And a lot of the research I want to do, the computers are not quite good enough to do what I want to do. And you have to do lots of tricks like this if you want to get things to be done in a reasonable amount of time. Okay, so this is some basic Babylonian mathematics, and we can begin to see efficiency coming into play. What I want to do now is I want to turn to the Fibonacci numbers. How many of you have not seen the Fibonacci numbers? Okay. If you do research with me over the summer, I actually start the Fibonacci numbers as 1, 2, 3, 5, not 0, 1, 1. There's reasons for that. Here we will do the standard definition. So Fibonacci numbers. And I'll give you some links to some interesting videos about the Fibonacci numbers to watch. So 0, 1, 1, 2, 3, 5, 8, 13. So we have this beautiful relation. Fn plus 1 is Fn plus Fn minus 1. F0 equals 0. F1 equals 1. This is called a difference equation, or a recurrence equation. This is extremely important. It falls in a lot of different categories. Difference equations are discrete versions of differential equations. So the most famous differential equation in the world.
I don't know which would be the most famous.
You're a physicist.
Which is the most famous, though? There are so many good ones.
No.
Laplace's equation.
No.
F equals ma.
F equals ma. F equals ma. Unquestionably. Most famous differential equation. The force is equal to mass times the second derivative of position. Basically, all of mechanics follows from this. Then there's different ways of formulating it, and there's different systems you can apply it, and what are the forces. But so much of the world is from solving differential equations. Difference equations are discrete analogs. So one of the examples that they give for motivating the Fibonacci numbers is, imagine you have your system of rabbits, and the rabbits are very considerate and they all reproduce at the same time, and the number of rats that reproduce is going to be a function of how many rats you have, or rabbits, or whatever you want to study. There's more interesting analogs of this you can do. How many of you have seen Star Trek 4? Is it okay if I ruin the plot a little bit? An alien probe is very upset that all the whales were hunted to extinction and is going to destroy humanity. So to save the planet, Kirk, Spock, McCoy, and the crew must travel back in time and bring back 2 humpback whales to the future to answer to the probe and explain to them that human beings are really, really, really sorry. Okay? So imagine we brought back... I could make watching this movie mandatory, but then I would lose people to build the Superstar Destroyer, so we'd switch to other sections. They really consider this to be a good plot for a Star Trek movie, and if you think this is bad, read the plot for Star Trek 5. Okay? So imagine you have wheels, and you want to know how many wheels do you have at a given moment in time. And so I'm going to show you how you can set this up as a difference equation. So again, we are going to do a lot more mathematics than we need just for Legos. I want you to see how this stuff can be applied. So imagine that wheels have a very simple life. They're born, and when they're 4 years old, they die. And we'll assume all wheels die at 4, no wheels are killed before they turn 4. We'll assume that when you're 1 year old, you're too young to have kids. And that maybe when you're 1 year old, you give birth to 2 pairs of kids. When you're 2 years old, you give birth to 1 pair of kids, and then you just enjoy the rest of your life. Okay? We can let AN be number of newborns in year n. BN be the number of whales 1 year old in year n, and so on. And so I can come up with equations. So if I want to look at AN plus 1, BN plus 1, CN plus 1, DN plus 1. And I want to figure out how many wheels do I have of each category. So how many wheels are there going to be who are born in year n plus 1? So I'm saying if you're 1 year old, you give birth to 2 pairs of wheels. If you're 2 years old, you give birth to 1 pair. It's going to be 0 AN plus 1 plus 2 BN plus 1 CN plus 0 DN.
Don't we need one wheel of each gender to make a pair?
Wheels, we're going to consider wheels a pair.
Okay.
And so when you give birth to a pair of wheels. We will not have wheels marrying or reproducing with their siblings. They will reallocate themselves. So this is a simplified model for wheels. In year n plus 1, how many wheels do we have that are 1 year old? AN. So it's just going to be 1 AN plus 0 BN plus 0 CN plus 0 DN. What about how many wheels that are 2 years old? I'm sorry?
AN minus 1.
That's one way to view it as AN minus 1. There's a better way to view it.
BN?
BN. And if I view it that way, I'm writing all of these in terms of my previous state, my immediately previous state. So 0 AN plus 0 BN plus 1 CN plus 0 DN.
1 BN.
1 BN? Sorry, 1 BN. And then similarly, DN plus 1 would be 0 AN plus 1 plus 0 BN plus 1 CN plus 0 DN. And then when you turn 4, you're dead. Okay? So here's a nice way to write down what's going on. And if you give me the initial conditions, I can just go forward in time and figure out how many wheels I have in each category. In the real world, you would not do anything as simplistic as this. You know, some wheels die early. Some wheels give birth to more pairs of wheels. Some give birth to less. You would replace these with random variables. What we can do is, how many of you have seen linear algebra? How many of you have not seen linear algebra? How many of you do not remember if you've seen linear algebra? Okay, good. Everybody has chosen. Alright, so I will occasionally say a couple of advanced things for people who've seen a little bit more mathematics. I can rewrite this using linear algebra. And I can write this in matrix form. And I can pull out all the ANs. This is why I was writing it like this. I can pull out all the BNs. I can pull out all the CNs. and I can pull out all the dn's. Eraser. And I can have this beautiful matrix like this, acting on an, bn, cn, dn. And so when I write like this is my transition matrix, and it tells me how many wheels I have in the next time frame from the previous. And in fact, if I call this matrix A, it would be the same as A squared times an minus 1, bn minus 1, cn minus 1, dn minus 1. And I can just keep propagating backwards in time. So for those of you who've seen linear algebra, all I have to do is compute high powers of this matrix and apply it to my initial conditions. Well, if you deal with high powers of matrices, the computations can actually become difficult. How many of you follow college football at all? You know, the scholar athletes from the different conferences. So this was the last year of the BCS system. Yes, I know. It is. I mean, I'm an Ohio State Buckeye fan. I know this is being recorded, but after what happened to Ohio State and what happened to Alabama, at least the right teams played for the championship. But the BCS system in college football has a lot of flaws in it. They're going to a playoff system next year. The colloquium talk this Thursday, every math stats major has to give a 30-minute talk to graduate, is going to be on ranking college football teams, ranking with incomplete information. And initially what happened is you have a certain number of people who vote, and you have this matrix and you keep iterating, and you see how the votes get distributed. And what was happening is some teams eventually were getting negative votes. And some teams were getting more votes than there were people voting. What happened is there were rounding errors because the matrices were so large, and we were taking such big powers because we have so many teams playing, that the algebra actually overflew the system and caused errors. So when you have big matrices, you can't just say, oh, well now if I want to see what happens in the 1000th year, I just calculate 8 to the 1000th. That's not necessarily an easy problem to do. And you have to figure out, how do I calculate high powers of this matrix? So just because we can write this down doesn't mean we can actually analyze this. And so what I want to give you an idea of, a sense of how you would attack problems like this. And so since not everybody has done linear algebra, I will show you how to solve this problem without using linear algebra. Just to connect this to the Fibonacci's, you can play the same game with the Fibonacci numbers as we did with the wheels. And so what you could do in that case is, if I give you fn plus 2, fn plus 1, fn plus 2, this is going to be 0 fn plus 1 fn minus 1. I'm sorry, no, 1 fn plus 1 fn minus 1. This will be 0. Let's see which way I want to do this. I think I want to do it this way. I will do the fn plus 1. I'll do it this way. Okay, so if I do it like this, fn is just 1 times fn. Fn plus 1 is just fn plus fn minus 1. So I can write this in matrix form. I can pull out the fn's and the fn minus 1's, and I can associate a matrix to the Fibonacci numbers. Oh, no, actually, if I'm writing it like this, I'm sorry, I guess I was writing the matrix like this. So again, I can just write down a matrix. I can reduce the Fibonacci number to just calculating a high power matrix. So what I want to do is I want to show you now how to solve this equation. One over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. So I call this the method of divine inspiration. Okay. If I give you a math problem and I give you a proposed answer, can you tell me if it's correct? Can you sometimes tell me if it's correct? What can you do? Plug. If you look at the Fibonacci numbers, what word would you use to describe all these numbers? Integers. If the joke I always make is if a Fibonacci number, mugs you on the street and you go to a police lineup and they have a bunch of numbers and you have to point to which was the number that did this to you. Does this look like an integer?
Yes.
Whoever said yes, you're a real mathematician. When you look at this, does this initially look like an integer? No, you've got square roots of 5, you've got divisions by 2. This should not look like an integer. We can check. When n equals 0, we get 1 minus 1 equals 0. When n equals 1, we get 1 over root 5, 1 plus root 5 over 2, minus 1 over root 5, 1 minus root 5 over 2. The 1's cancel. We get root 5 over 2 plus root 5 over 2 is root 5. The root 5's cancel, and we get 1. And then if you know mathematical induction, you can check and show that this actually satisfies the recurrence relation. And this will be a solution. The method of divine inspiration, however, is tough to count on. Right? It's very hard to always look at a problem and know what the answer is. In this case, I can actually get it. There are other ways to guess what the answer is. And for those of you who are interested, I think basically due to in the interest of time, I won't go through the video today. I'll let people email me if you want to watch the video at home, that's fine. If you want me to show the video in class tomorrow, happy to do that. But there's ways to find this formula without being divinely inspired. And in fact, you can use that to solve other recurrence relations, other difference equations like this. Okay? What I want to do is I want to really talk about this formula. So this is known as Binet's formula. How many of you have seen Binet's formula before? Okay. How many of you have seen the Fibonacci numbers before? Okay. What is the advantage of Binet's formula? Why is it so wonderful?
You don't need to know the previous ones?
You don't need to know any of the previous ones. If somebody really cares about the 1,000,000th Fibonacci number, you can jump to the 1,000,000th Fibonacci number. That's much better than going through your whole list. So in terms of solving questions, for a lot of things, this is a much better way to go, to use the Binet formula than to go through the sequence. What might be a difficulty of Binet's formula? Yes? Yeah, how do you actually calculate something like this? Because we don't want to put this into our computer and have rounding errors. We're supposed to get a nice integer. Well, to some extent, if I can calculate things very close to an integer, I know the Fibonacci numbers are integers. I just have to get within 0.5. And then whichever, if my error is less than 0.5, I just go to whichever integer is within 0.5 of it. Can somebody tell me roughly how big is 1 plus root 5 over 2?
6.
I'm sorry? About 1.6. What about 1 minus root 5 over 2? Negative...
Minus 0.6.
Negative 0.6. So if you raise negative 0.6 to a huge power, this is very small. If you raise 1.6 to a huge power, it's very large. Essentially, the nth Fibonacci number is whatever integer is closest to this. This little correction here actually forces you to be an integer. So what I want to do is, I know a lot of you have seen stuff like this before. I want to show you Binet's formula in a way you may not have seen. Alright, so I want to calculate something like this. You've all done Calc 1. The question is, have you done Calc 1 correctly? Alright, this is a dangerous question to ask. What's the derivative of x squared? X cubed. 3x squared. X to the 4th.
4x.
X to the 3 halves.
3 halves. 3 halves.
3 halves x to the 1 half. X to the 5/7.
5/7. X to the negative 2/7.
Okay, well, almost in unison. Come on, be like the Borg. X to the root 2.
2.
And 2 to the root 2 minus 1.
What does x to the root 2 mean? You know its derivative, great. What does it mean? Something like x squared, I know what that means. Take x, multiply by x. Okay, I can understand that. X to the 1/2, I can understand what that means. I'm looking for, x to the 1/2 equals y is the same as y times y equals x. I'm reducing the problem to an integral number of multiplications. I can understand x to the 1/2 equals y. I can understand x to the 3/2 equals y. If I gave you x to the 3/2 equals y, then I want y times y to be x times x times x. I can understand a problem like that. What does it mean to raise something to the root 2th power? So you've all been, you can all yell out the answer, but what are you actually manipulating? And this is one of the dangers in mathematics. It can become so rote, it's easy to forget how you actually do things. And how do you actually prove these results? One thing you can do is we understand rational powers. So if I give you something like x to the root 2, I can look at x to the 1, x to the 1.4, x to the 1.414, and basically take bigger and bigger rational approximations to root 2. All of those make sense. And from those, I can then interpret x to the root 2. The best way is x to the root 2 is e to the root 2 log of x. And use the infinite series expansion for e to make sense of something like x to the root 2. I promise you, this is connected to the Fibonacci's and efficiency. Okay? This is a well thought out, prepared lecture. Okay? What is the connection? How do you calculate the derivative of x squared, x cubed, x to the 4th? How did you prove that? What did you use? How did you find the derivative of x squared or x cubed? Going all the way back to your Calc 1 days.
Rules we memorized.
D-A-Y-S, not D-A-Z-E. How did you prove them? I'm sorry? Limits. And so how did you evaluate? So you have, f of x is x squared. F prime of x, well, let's do x to the n is an integer. F prime of x is the limit as h goes to 0 of x plus h to the n minus x to the n over h. How do we calculate this? How do we calculate x plus h to the n?
Binomial.
Binomial theorem. So we use binomial theorem. And that's x plus y to the n is the sum, k goes from 0 to n choose k, x to the n, x to the k, y to the n minus k. So we use the binomial theorem, we expand this out. You actually don't need the full strength of the binomial theorem. All I need to know is that when I expand x plus h to the n, the first term is x to the n, which cancels with that. The h term is n, x to the n minus 1h. And then all the other terms have at least an h squared. I don't care what the coefficients are. That's enough to prove the derivative. So you don't need the full strength of the binomial theorem. That's how we can actually evaluate something like this. I can use the binomial theorem to attack 1 plus root 5 to the n. And so if I use the binomial theorem, I would get 1 over root 5, the sum, k goes from 0 to n of, now I gotta figure out how I want to write this. I'll write this as n choose k, 1/2 to the k, root 5 over 2 to the n minus k, and then minus 1 over root 5, the sum, k goes from 0 to n, of n choose k, 1/2 to the k, negative root 5 over 2 to the n minus k. And so I can use the binomial theorem to expand this out. What do you notice when I start looking at this expansion? Does every term survive and contribute?
No.
No. When n minus k is even, the terms cancel. So you only have to worry about n minus k being odd. And the other thing that's really nice is I'll have root 5, then 5 root 5, 25. I'm going to always have an integer or an integer times square root of 5. So at the end of the day, when the dust settles, I'll get something that looks like this. A plus b root 5. So if I want to calculate this, I can calculate it exactly and get a perfect answer. So this satisfies step 1. It is a way to solve the problem. In a research project I'm doing with some of my former students right now, it turns out this is too slow to be practical. The sum over here takes too long to do. I need to work with 200,000 digit Fibonacci numbers. My n is huge. And it just takes too long for the computer to actually calculate these sums. And so it becomes a very interesting question as to how would you do this in greater detail. So I don't want to go into too much depth on the mathematics. I just want to give you some sense of what the issues would be. If I have a formula like this, theoretically, I'm great. But from a computational perspective, it's very bad. What we needed to do is we actually needed to calculate these sums almost inductively, recursively. And so we calculated the first term, and then we saw how much different was the second term from the first term. And we basically kept updating what our term was. And so you can figure out, how do I go from one binomial coefficient to the next, to the next, to the next? And I would just multiply by coefficient by that, save it into memory, and keep updating like that. This led to easily order of magnitude speeding up in terms of the runtime. But sadly, this was not fast enough to be practical. It actually was fastest to go all the way back to the beginning and use the damn stupid recurrence relation. The problem is, we then needed to save the output to a file to speed things up. And so the computations became one-time, very cost-intensive. So again, it's very cheap to calculate the Fibonacci numbers from the recurrence relation. But to store them, it then becomes very expensive for storage issues. So again, I want you to leave this class with a sense of what are the issues when you try to apply mathematics to the real world. For a lot of the problems you're looking at, very quickly you get into calculations that are just beyond what your system can do. And you have to find clever tricks, clever ways to deal with all the different systems. Okay. I'm not going to really go into other ways of solving the Fibonacci's. You know, if you're interested, let me know. I can give you some stuff to read about generating functions, which is another great way of attacking problems like this. There's a lot of good mathematics, but there's enough stuff here to drive home, one of the major themes of the class. Just because you can do something one way doesn't mean you should do it that way. It's a search for efficiency. And so Binet's formula allows us to jump. But just because we jump doesn't mean we can actually execute the jump. Okay? And so again, if you're really interested, I'm happy to talk to you in greater detail about how would you handle this sum in a clever way. How would you have your incremental counters that you're building up? I guess I'll just do one small term, and then we'll move on to something new. So let's say you have n choose 2, or more generally, n choose k is defined as n factorial over k factorial n minus k factorial. How many of you have not seen binomial coefficients like this? How many of you have not seen n choose k? Okay, so we can talk at some point.